Alright, we'll start now our sample problem for the tension members. Now the problem says that we have to determine the design capacity of the tension member as shown below. Now we have this tension member and they're actually lap spliced. Then this is the layout of the, let's say the connection, the bolted connections. So we have this actually two members, one let's say at the bottom and then one on top, and we're actually applying a let's say a tensile force here. Okay, so let's say we have this P, and here of course we can draw it here. Now of course if there's gonna be a different thickness, let's say this member at the bottom is or will have a different thickness than the member on top, then of course there's going to be a different computations for that. We have to check that as well. But here we're just given with the same thickness, and the problem says we have an A36 plate 200 by 12 mm. So meaning the width here from this, let's say from this edge to the bottom point, or to this bottom edge, that's 200 mm, and our thickness, and that will correspond to this will be the 12 mm, and it says we have a 616 mm diameter, 8325 bolts. Okay, so take note, if we have a 16 mm bolt diameter, then our bolt hole would be 2 mm larger. And for A36, this is, okay, so this Fy and Fu, they're actually true for A36 steel. Okay, so let's solve now the capacity based on the yielding of the gross area. So let's say solving for the capacity based on yielding in gross section. Okay, so our equation is the factor capacity is equal to the reduction factor times the yield strength of A36 times the gross area. By the way, it's there's also, I mean, it's also possible that the failure would be on the bolt connection itself rather than the plate, but that's gonna be our topic next week. Now we'll just focus for now. We'll just focus our failure would be on this tension member. So to continue, we have this our equation that the factor capacity is equal to the reduction factor, which is 0.9 times the Fy, the given yield strength is 250 megapascals. So let's write it here, 250 megapascals times the gross area. Now our gross area is just, since this is just a plate, let's say a flat bar, then it's just 12 mm times 200 mm times 12 mm. And if you do the math, what you'll get is 540 kilonewtons. By the way, your unit that you'll obtain here, megapascals, that's in newton per mm squared, and you multiply that to mm squared and then convert that to kilonewton, or divide that by 1000, and you get this answer, 540 kilonewton. Now the next one is, let's say, solving for the capacity based on, um, say, the fracture in the net section. Okay, so in the net section we have, I think it would be better if we'll solve separately the area. So A net is equal to the gross area times, not times, that's minus the number of bolts, of course in that section only, times the area of bolt. Right, so A, B. Okay, so what's our gross area? That's just 200 times 12, and that's 2,400 mm squared minus, I guess we have to draw it here. So let's say this is our figure. Okay, and this is our center line. Okay, so the this diameter right here, this is actually the diameter of the hole is equal to, since we have 16 mm, that's 16 mm plus 2 mm. So for now, let's just use this clearance, because later on there's going to be a specified value for the hole. That's on when we get to the topic on bolted connection. Okay, so this is our bolt hole diameter, and that's 18 mm. Now for the thickness, we have 12 mm. So therefore, area of the bolt would be, the area of the bolt would be 18 times the thickness, which is 12. So 80 times 12, that's 216 mm squared. And the number of our bolt hole is, okay, this is 1, then 2. Okay, so to solve, we just have 2,400 mm squared minus 2 times 216 mm squared. Okay, times 2. And that's 1968, 1968 mm squared. So that's our net area. Now let's apply the equation for the limit state. That's going to be the reduction factor times the ultimate strength times the net area. Now for this fracture in the next net section, we have this one. This reduction factor is 0.75 times the ultimate strength, which is in this F sub u is what was it, 410, okay, 410 megapascals, okay, times the net area, which is 1968 mm squared. Okay, so to solve that, then we can just, okay, 0.75 times 410 times 1968, that's gonna be 605 point, let's say 0.2 kilonewtons. Okay, so this is our answer for the two limit states. Now we have to check the third limit state. Okay, so first we'll draw the let's say we'll draw first the different failures, and I'll just have to pause this video to save the time. Alright, now I'm already done with the figure for the block shear failure. Now we have these three possible failures. Now here in failure 1 we have the outer chunk or outer block is actually failing, and then this one, the centerpiece, is the ones that's ripping apart, and here the failure is only on this chunk. Okay, so in calculating this block shear failure, we have, I think it's first systematic if we solve for the specific area, like for example the net area for shear, and then once we have those values, then we can just simply substitute that in our equation, and then we can solve for the value of the capacity. Okay, so recall that our bolt area here in the figure, we have a 216 mm squared, and that depends upon the number of bolts. Now for here, of course, the number of bolts, for example in the shear, then the number of bolt holes would be, for example, this one, 2, and this is actually failing at the center, so meaning it's just like 0.5, one half of the bolt diameter. Okay, so that's going to be 2.5. Okay, so now let's solve. We have this step number 3, solving for block shear capacity. Failure 1. Okay, so our A gross area, AGV, our gross area for shear. Now we have two shearing planes here, so one here, and then the other is this plane. Okay, so 1 and 2. Now the area, let's solve first for the area here on one shearing plane. Now we have a bolt, or let's just solve first for the I think that's the cross area first. Okay, so we have this length. What is this length? That's going to be 50 plus 75 plus 75, and this will be 200. And our thickness is, we have a 12 mm thickness. Okay, so that's going to be 200 times 12. Okay, times, since this is a cross area, then we don't need to subtract the bolt holes. 200 times 12 times, there's another shearing plane here, then that's going to be 200 times 12 times 2. That's going to be 4,800 mm squared. Now for the net area in shear, for the net area in shear, that's just going to be, okay, this one, this length right here, that's the area, that's 200 times 12. 200 times 12, that's just 2,400. Okay, so we can do it this way. We're just starting with the length, or I mean the area, minus the area of the bolt hole, or I guess we can just use this one. Okay, so that's 4,800 mm squared minus the area of the bolt. So you notice the area here, we have one, okay, one hole. This is one hole also. This is one half, and this one is this would be one half as well. So I think 1/2 plus 1/2, that's 1. So we have 5. 5 times the area of the bolt, which is 216 mm squared. Okay, so minus 5 times 216, that's going to be 3,720 mm squared. And then lastly, we have to solve for the area in the net tension. Now the net tension is this one. So if it's a net tension, then we have to subtract the value here. First, let's solve for the gross area of the tension. So that's going to be 50 plus 50. That's going to be, or we can just write 50 times the thickness, 12 times 2. And that's going to be minus the number of bolts, so 1/2 plus 1/2. So that's just 1 times the area of the bolt. Okay, so if you solve 50 times 12 times 2 minus 216, that's going to be 984 mm squared. Now we'll apply the equation for shear. This is our equation. So phi Rn is equal to the minimum of phi times 0.6 Fy AGV plus U Fu, then A and T. Okay, or the other condition can be 0.6 Fu in the net shear plus U Fu A and T. Okay, so I guess we'll have to solve first separately so that we can save space. So 0.6 Fy AGV, that's gonna be 0.6 times the Fy, which is 250 megapascals, times the gross area, which is 3,720 mm squared. You get 0.6 times 250 times 3,720. That's going to be 558 kilonewton. And for 0.6 Fu A and V, that's going to be 0.6 times this is 410 times the area of shear. Oops, sorry. This one should be here, 3,720. This one should be the 4,800. Okay, so 0.6 times 250 times 4,800, that's 700. This is 720 kilonewton. Now this one, 0.6 times 410 times 3,720, that's 915 point, let's say 0.1 kilonewton. And for our second term, U, F, U, A, and T, this U is just equal to 1. Then F, U is 410 times the net area, which is 984. So 984 times 410, that's going to be 403.4 kilonewtons. Okay, so now let's substitute all the values. Phi Rn is equal to the minimum of, okay, so let's apply the reduction factor, which is 0.725 times this term, which is 720, plus this term, 403.4, or this term 915.1, of course you have to apply the reduction factor, that's 0.75, or let's write it again, 15.1 plus 403.4. Okay, so 720 plus 403.4 times 0.75. That's going to be 842.55 kilonewtons. And this one is 915.1 plus 403.4 times 0.75. That's 988.8 88 kilonewtons. So the minimum is 842.55 kilonewton. Now, of course, that's going to be based on this block shear mode of failure. And for another failure that we have to check again, and for the third failure we have to do the checking again. Okay, so for the second one, okay, so let's say solving for block shear capacity, that's going to be failure 2. Now here it so happened that since we have a something like a symmetrical dimensions, then this failure 1 and failure 2 will have actually the same values for the shear area, then the tension area. As you notice here, for example, the tension area is just 50 times 12. So 50 because we have 50 here on top and then 50. Oh no, sorry. I think this is the 50 times 12 times 2. So actually 50 times 2, that's just 100. And here, even though we only have one area, it's just 100. So they're actually the same. So we don't need to calculate it again because it will just yield to the same value. Now for the last failure, so let's say failure 3. Okay, so our gross area in shear, we have this shearing area, which is just actually 200 times 12, because this 75 plus 75 plus 50, this is just 200. Okay, so 200 times 12 is equal to 2,400 mm squared. Now for the net would be 2,400 minus the number of bolts. So we have 1, 2, and there's 1, 2, and 0.5. So that's going to be 2.5 minus 2.5 times the area of bolt, which is I think that's 216 mm squared, minus 216. That's 1,860 mm squared. Okay, so the next is the tension, the net tension area. That's 100 plus 50. That's going to be 150 times the thickness minus the number of bolts. That's 1 times half of this, so 1.5 1.5 times 216. Okay, so 150 times 12 minus 1.5 times 216. That's 1476 squared. Now if we solve for the 0.6 Fy AGV, it's going to be 0.6 times 250 times 2400, 0.6 times 250 times 2400. That's just 360 kilonewton. The other one, 0.6 FUANV, 0.6 times 410. There's the shear area, 1860. 0.6 times 410 times 1860. That's 457.6 kilonewton. And the last term is FUANT. It's just 410 times the area, which is 76 mm squared. 410 times 14, 76. That's 605.16 kilonewton. Okay, so now we can solve VRN is equal to minimum of 0.75 times this one, 360 plus 605.16, or 0.75 times 457.6 plus 605.16, and we get 360 plus 605.16 times 0.75. That's minimum of 723.87, and the other one is 457.6 plus 605.14 times 0.75. That's 797 kilonewton. Okay, so therefore phi Rn is, the minimum is 723.87. Now we have actually solved the various capacity based on the different limit states. Now actually the design capacity would be, okay, so this is 4, 5, this is 6. So the design capacity is the minimum. Okay, VPN is just simply the minimum of the four values. Now for the yielding in the cross section, we have 540 kilonewton. Then for the fracture in the net section, we have 605.2 kilonewton. And for our first failure in block shear, we have a value of 842. Let's say 842.55 kilonewton. And what else? The second value for the block shear is 723.87 kilonewton. So therefore VPN is equal to 540 kilonewton. Okay, so just to review on what we did, we're actually analyzing the problem, or let's say this is an analysis problem. We're given the geometry, we're actually given the geometry and the details, and we are to solve for the capacity. So first what we did is to solve for the first limit state for the yielding in the cross section, and we just apply this equation directly and take note of this reduction factor, which is 0.9. and we obtained a value of 540 kilonewtons. Now for the fraction in the next section, we just apply again the if we apply this equation, we have to solve. We separate the computation for the net area because that would be systematic, I think. So the net area, this is the net area, and then we just substitute the values and we obtain this. The For the third limit stage, we can actually have various modes of failures, and we have to check all those modes of failures. Now for the mode failure 1, we just first solve for the shear area, the net area for shear, and the tension, net area for intention, because that would, I think, simplify the space for the computation. And then we substitute it to the equation. We solve this 842. Then another failure, we check, and we got the value 723. The capacity would be the minimum of the limiting states, the value obtained from the limiting states, which is 540. Right. Now in the next video, we will discuss in details what if we have a staggered pole connection. Now, instead of having an inline connection like this, what if the tap row is staggered? It's not actually in line with this. Then what's going to be the capacity, or what's going to be the effect in the capacity of the section? And as well as other details, we will discuss that in our next lecture. So see you in the next video.